Welcome to this installment of the Deep Dive.
Great to be here.
And yeah, big hello to our Tech Unplugged database series.
Absolutely.
So you've given us this really fascinating collection of information on graph databases. And our mission today really is to unpack it all. We want to give you the key ideas, those sort of aha moments.
Without getting totally lost in the technical jargon.
Exactly.
Yeah.
Think of it as a shortcut. And yes, we should mention this deep dive is AI generated.
Right. Synthesized from all the material you provided, bring together the core findings.
So we won't be listing specific websites or documents today.
Nope. The focus is really on a comprehensive analysis, the concepts, the findings across everything.
Okay, so let's get right to it. Graph databases.
Yeah.
What exactly are they? What makes them different?
Well, at its heart, a graph database is all about structure,
Yeah.
but specifically how data connects.
Connections.
Yeah, instead of, tables with rows and columns like you have in relational databases, it uses nodes.
Nodes. Like points.
Exactly. Nodes represent things, could be users, products, account, anything really.
Okay.
And then you have edges, which represent the relationships between those nodes.
Ah, so the lines connecting the points. Like friend of or purchased.
Precisely. And what's really key is that these relationships aren't just like implied by matching keys in different tables. They're explicitly stored. They're first-class citizens.
Okay, stored as connections.
Right. And both the nodes, the things, and the edges, the relationships can have properties,
Properties.
just extra details, key value pairs, like a user's name or the date a purchase was made.
Gotcha. So it's really built around these explicit links then.
That's the core idea.
So how does that translate into like real world advantages? Why do it this way?
Well, because those connections are stored directly, querying them becomes incredibly efficient.
Faster queries.
Much faster, often, especially when you need to explore those relationships. Retrieving related data can often be a single operation. You just sort of follow the path.
All the edges.
Exactly. This is super powerful when you've got data that's heavily interconnected.
Like what? Give me an example.
Okay, think about something complex, like trying to spot a sophisticated money laundering ring.
Okay.
You might have thousands of transactions that look totally unrelated in a normal database.
Right. Separate entries.
But in a graph database, you can potentially trace the flow of money through multiple hops, uncovering hidden links much, much faster.
Ah, so you can actually see the web of connections.
Precisely. And that can help you stop illegal activity much sooner.
That makes a lot of sense. Now, most people listening are probably familiar with traditional relational databases, SQL and all that.
Sure, the standard for decades.
So what are the big benefits of using Graph instead? When would you choose it?
That's a really critical question. For data sets where the relationships are the main event, graph databases often just perform way better.
Better speed.
Significantly faster, yeah. Think about that social network example again. Finding your friends is easy in either system.
Yeah.
But what about finding friends of friends or friends of friends of friends, going several levels deep?
Okay, yeah, that sounds more complex.
In a relational database, that involves multiple join operations, linking tables together based on keys.
And joins can be slow, right?
Yeah.
Especially with lots of data.
They can become incredibly expensive, computationally speaking, but in a graph database, those connections are already physically there, in a sense.
So traversing them is quicker.
Much quicker. We're talking about a potentially massive difference. It's not just academic. It impacts user experience directly. Real-time results versus, well, waiting. Or timeouts.
And it's not just speed, is it? Something about handling large data sets, too.
You're right, scaling. Graph databases often scale more naturally with huge data sets.
Why is that?
Largely because meaning it's often better suited for managing data that changes a lot, where the structure evolves over time. That's pretty common today.
Okay. You mentioned that social network example in speed.
Mhm.
Were there actual, like, benchmark tests in the materials?
Yes, absolutely. Some really compelling ones.
Like what?
Well, one comparison ran a query looking for connections 5 degrees deep. So friends of friends of friends of friends of friends.
Wow, that's deep.
Yeah. The graph database nailed it in seconds.
Seconds.
While the relational database either took an incredibly long time or it just timed out, couldn't even finish the query.
That really paints a picture. It highlights the performance difference dramatically.
It does. It comes down to that fundamental difference in linking data. Relational uses foreign keys, requiring joins. Graph uses direct pointers, essentially.
So this sounds like quite a shift from the traditional way of thinking about databases.
Hmm.
What prompted this? Why did NoSQL and Graph emerge?
It was really a response to the challenges of modern data, the sheer volume, the speed it comes in at, the variety, big data, basically.
Right, the V's of big data.
Exactly.
Sure.
Traditional relational databases, while fantastic for structured data, think things that fit neatly into tables, like paper forms digitized.
Yeah, inventory, customer lists.
They started to struggle with modeling the more messy, ad hoc relationships you find in the real world,
Messy relationship.
like social connections, influence networks, complex dependencies. Trying to force those into tables often leads to these huge, unwieldy join tables.
Performance tanks.
Performance tanks as the complexity grows. Graph databases offered a fundamentally different approach, one that's naturally suited to these interconnected scenarios.
So if you've ever been frustrated by slow queries on connected data in a traditional system.
Graph databases might be the solution you were looking for.
Okay, so we get the what's and the why. Let's talk applications. Where are these things actually being used out there in the wild?
Oh, lots of places now. Social networks are the classic example.
Like Twitter, Facebook.
Exactly. Hundreds of millions, even billions of users' nodes and their connections following. Friends, those are the edges. Perfect fit.
Makes sense.
What else? Recommendation engines.
Huge area.
Like, customers who bought this also bought.
Precisely that kind of question. In a graph, finding products frequently bought together by users who bought a specific item is a pretty straightforward path-finding query.
As opposed to complex joins and relational.
Right, which means faster, more relevant recommendations for you as a user.
Okay, social recommendations. What about less obvious uses?
Fraud detection is a really big one, and quite fascinating,
How does that work?
because graph databases excel at finding those hidden connections. Seemingly isolated accounts or transactions might actually be linked through a series of intermediaries.
Ah, so you can spot patterns that look innocent individually but are suspicious when connected.
Exactly. Identifying rings, synthetic identities, unusual flows of money, stuff that's hard to see in rows and columns.
That's powerful. And cybersecurity is another rapidly growing field for graphs.
Really? How are they used there?
You can model your entire IT infrastructure as a graph. Servers, applications, users, data stores are nodes, connections, access rights, data flows are edges.
A digital twin of your network.
Kind of, yeah.
Yeah.
Then you can run queries like, show me all users without multi-factor authentication who have access to sensitive databases.
Wow. Or find data stores that aren't being backed up regularly.
Exactly. You can identify critical assets, track attack paths, analyze vulnerabilities, see the potential blast radius of a compromised machine.
So you can use graph algorithms to find weaknesses and prioritize fixes.
Precisely. It helps you see the bigger security picture.
That's incredibly clever. I wouldn't have immediately thought of that for graph. What other areas?
Well, logistics, real-time route optimization for deliveries.
Finding the best path for parcels.
Yep. Managing metadata for media content is another one.
Metadata.
Yeah, like linking actors to movies, movies to directors, genres, user ratings. It's all interconnected. Financial services use them for managing entitlements, who has access to what data or system.
Okay.
And really diverse industries, healthcare, retail, oil and gas, even gaming.
It really sounds like they're popping up everywhere. I think I also saw something about AI and machine learning.
Yes, that's a really important synergy. Graphs can provide crucial context for AI.
Context.
By connecting disparate data points data that might live in different silos. Otherwise, graphs can help AI models make more context-aware predictions. Understanding the relationships around a data point makes the AI smarter,
So better predictions.
better, and often more explainable predictions. This is huge for explainable AI or XAI.
Explainable AI, meaning you can understand why the AI made a certain decision.
Exactly. The graph can often show the path, the connections, the evidence that led to the outcome, which builds trust and allows for debugging.
That's critical in many fields.
Absolutely. And one more practical application, compliance, like GDPR.
Data privacy regulations.
Yeah. A graph can make it much easier to find all the places where a specific person's sensitive data resides across your systems because you can model the connections.
So you can apply rules consistently or delete data properly when requested.
Exactly. It helps manage that complexity.
It's really quite something how focusing on the connections changes what's possible.
It really reframes the problem in many cases.
Okay, this is fascinating. You mentioned nodes, edges, properties earlier. Are there other key graph concepts we should probably touch on?
Yeah, a few more terms pop up. The labeled property graph, APG model, is very common.
Labeled property graph.
It just formalizes what we discussed. Nodes and relationships can have labels like customer or product or purchase to categorize them.
Okay, labels for types.
And they both can have properties, those key value attributes like name, Alice, or amount, 50.
Got it. What about actually getting data out? Query languages.
Right. There are several, but Cypher is a well-known one, often associated with the Neo4j database, but the concepts apply more broadly.
Cipher, like deciphering?
Kind of. It's designed to be quite expressive and uses ASCII art, sort of visual patterns, to describe the graph structures you're looking for.
Visual patterns, like drawing the connections.
Almost, yeah. You use clauses like match to specify the pattern of nodes and relationships you want to find.
Mass.ch.
Okay.
Then return says what parts of that pattern you want to get back as results.
Return. Simple enough. There's also create to add new nodes and relationships. Merge, which is clever. It tries to match an existing pattern, but if it doesn't find it, it creates it.
Ah, like an upsert in other databases. Find or create.
Sort of, yeah. And where for filtering results, similar to SQL.
That math.ch part sounds quite intuitive, visually asking for the shape of data you need.
It can be, yes. Makes graph traversal logic clearer sometimes. Another key technical concept is index-free adjacency.
Index-free adjacency. Sounds efficient.
It is extremely. Some graph databases implement it so that connected nodes literally have direct pointers to each other at the storage level.
Physical pointers.
Yeah. So traversing from one node to a directly connected neighbor is incredibly fast, often what's called O1 or constant time.
Meaning the speed doesn't really decrease even if the database gets huge?
For that specific step, yes. The database is sort of pre-wired. It doesn't have to look things up in a separate index to find the next connected node.
That must be a core reason for their speed in relationship-heavy queries.
It's a huge factor. Then there are some concepts often borrowed from social network analysis that are relevant.
Like what?
Triadic closure. It's the principle that if you have two friends in common with someone, you're more likely to become friends with that person too. The triangle closes.
Ah, the friend of a friend effect, used in recommendations.
Often used in predictive analysis, yeah. Recommendations, community detection.
Interesting. What else?
Structural balance theory talks about stability in networks based on positive and negative relationships. Think, the friend of my friend is my friend, the enemy of my enemy is my friend. Patterns like that.
Okay, analyzing network stability.
And local bridges. These are relationships, edges, that connect otherwise distant parts of the graph. If you removed that edge, the shortest path between those two nodes would get much longer.
So connections between different clusters or communities?
Exactly. Often represents links between different social circles or different departments in an organization or different fields of knowledge. Identifying them can be important.
These are really neat concepts, especially seeing the link to social science. So with all this power and these interesting ideas, should everyone just ditch their relational databases and switch to graph?
Whoa, hold on. No, not necessarily. The information we reviewed was pretty clear on this.
Okay.
You shouldn't switch just because graph databases are cool or trendy. There needs to be a real demonstrable benefit. Like significant performance improvements for your key queries, lower latency that actually matters for your application. Evidence is key.
So choose the right tool for the job.
Exactly. And security, of course, is just as critical with graph databases as with any other database.
Especially with potentially sensitive connected data.
Right. All the standard best practices apply. Encryption at rest and in transit, strong access controls, multi-factor authentication is crucial.
Regular backup.
Regular backups, keeping database servers separate from application servers, all the usual important stuff.
Yeah. And I think there was a mention of different types of graph systems. Something about transactional versus analytical.
Ah, yes. That's an important distinction. You generally have transactional graph databases, often called OLTP systems.
OLTP. Online transaction processing.
Right. These optimize for real-time operations, lots of reads and writes happening quickly. Think adding a like or a follow on social media, processing a financial transaction that needs relationship checks.
Okay, for live applications.
Then you have analytical graph compute engines, or OLIP systems.
Online analytical processing.
Yeah. These are designed more for large-scale batch analysis on the entire graph or large parts of it, running complex algorithms to find global patterns, community detection, influence analysis.
So more for analysis and reporting than real-time interactions.
Generally, yes. The choice between OLTP and OLAP depends heavily on your primary use case. Some systems try to blend capabilities, but often there's a focus.
Makes sense. And what about keeping things running? High availability.
Also crucial for many applications. Graph databases typically achieve high availability, HA, using clustering and replication.
Spreading the data across multiple servers.
Exactly. So if one server node fails, others can take over, ensuring the database stays operational. Standard HA techniques adapted for the graph model.
Okay, great. So let's try to sort of wrap this up. Let's unpack what this all really means.
Yeah, the big picture.
As you can clearly see, the database world keeps evolving. And graph databases, well, they offer a genuinely powerful, different way to look at data, especially interconnected data.
It's a paradigm shift for certain kinds of problems.
From powering the social networks we use every day, to fighting fraud behind the scenes, boosting cybersecurity, even making AI smarter.
Their strength really lies in navigating those relationships efficiently.
Unlocking insights that, frankly, are often really hard or slow to find using traditional tabular methods.
Definitely.
Now, we've really only scratched the surface in this deep dive. There's a lot more detail, of course.
Oh, absolutely. Each of these areas could be its own deep dive.
But hopefully you, the listener, now have a much clearer handle on the potential of graph databases and the key ideas driving them.
The core concepts, the use cases, the why.
And this focus on interconnectedness, it really mirrors how complex the real world is, doesn't it?
It does. Data rarely lives in perfect isolation. These databases try to embrace that complexity.
Which opens up some really exciting possibilities for how we manage, analyze, and ultimately understand information moving forward.
For sure.
Well, thank you for taking this deep dive with us today.
Thank you.
Stay tuned for more explorations into the fascinating world of technology. Thanks for listening. Stay tuned.